Mm-hmm.
And Akash, go ahead.
Do you see my presentation?
Yes, I can.
Sure. Good morning, everyone, again. As I mentioned, my name is Akash Ashapure, and I'm a doctoral candidate in geomatics engineering at Department of Civil Engineering, Purdue. And the topic I'm going to be covering today is portion of my PhD research, which is going to be machine learning based high throughput phenotyping framework for cotton crop yield prediction using multimodality remote sensing data. Recent years have witnessed enormous growth in the application of unmanned aircraft systems in precision agriculture, mainly because of their flexible availability, their low cost relatively, and high spatial resolution. And crop yield estimation is very important for precision agriculture as it helps manage the fields and take economic decisions. And the current manual approach that people adopt for crop yield estimation, the manual approach, it is time consuming, it's labor intensive, and it is expensive. And a lot of research has been done in the area of UAS based plant phenotypes being used for crop yield prediction. But unfortunately, full potential of UAS has not been exploited in the literature to estimate the yield. So to this end, over a research plot, cotton research plot in Texas A&M AgriLab Research and Extension Center at Corpus Christi, we collected UAS data on a weekly basis using RGB and multispectral sensors, along with the ground control points. Then we use these raw input images and provide it to the structure from motion photogrammetry software, and then we get the orthomosaic and digital elevation model. And then in the next step, we compute plant attributes and vegetation indices, such as canopy height, canopy cover, canopy volume, and vegetation indices like excess greeniness index and NDVI. In the next step, we prepare the data so that we can provide input to the machine learning model. So that involves concatenating all those temporal canopy attributes and vegetation indices. And we also use some non-temporal features such as open cotton boll attributes that we see from the aerial images towards the late season. And we also included those in the concatenated feature vector. In the next step, the feature vector that we prepared, we feed it to the artificial neural network architecture to predict the yield. And here are the training and test R-square results. The correlation suggests that the R-square of 0.89 for the test set and 0.93 for training set. We also compared our results with, I'll quickly turn on the pointer.
Very high correlation.
Yes, and we also compared our results with support vector regression and random forest regression. And we noticed that both of them, however, performed not so good compared to artificial neural network, but they also had pretty high R-square for test set. Coming to the large scale cotton crop yield prediction, although unmanned aircraft systems provide high spatial resolution, their revisit time is really flexible, but they suffer from limited flight time, and their data storage overhead is also high, and you can only cover small area. On the other hand, if we consider satellite data, the spatial coverage is really large, but it provides coarser spatial resolution. So there is one research area where we found this gap where the objective of this particular research is crop yield estimation by computing UAS, combining UAS and satellite data to take advantage of both the technologies. So to this end, the scope of this research is to be able to use multi-temporal satellite data, and then we provide it to a deep learning architecture to predict the crop yield. But here the question is how efficiently we can utilize the limited available UAS-based features to improve yield prediction accuracy. So to this end, initial experiments were performed setting up the baseline experiment that utilized only the multitemporal satellite data. We provide it as input to the machine learning model and we predict the yield. And we noticed that the test R square turned out to be 0.68. So it's pretty decent, but as compared to when we saw in the previous results where UAS data was input, there's a lot of scope for improvement. So we assume that providing UAS-based information is certainly going to improve the results. So there are two ways where we can, in which we can utilize the limited available UAS-based information. So the first way is to utilize the UAS-based canopy attributes as side information as part of the input, along with the multitemporal satellite data. And the second approach is using UAS-based canopy attributes as one of the target. So talking about the initial approach first, which takes UAS information as input, part of the input, we kind of adopted um, the approach that people have been using for depth and RGB fusion. So it requires UAS-based canopy attributes to provide to the model at the time of input. So the way it works is at the time of training, we provide the satellite data to the satellite network that consists of bunch of neural network layers, and we also provide UAS-based canopy attribute to a different network. And then after some features, we fuse these features and we process through more layers of neural networks, and we try to predict the yield. But what we also do at the same time is introduce this third network, which tries to mimic the UAS data network at the time of training by introducing the hallucination loss. So the assumption here is after training, we should be able to have this hallucination network trained enough to mimic the UAS data network so that we can discard UAS data network at the time of testing and then replace it with the hallucination network. And then the implementation results are impressive. It's a huge improvement compared to using satellite data alone with a test R. Sorry about the misspelling. It should pronounce as testing. So with the test R square of 0.77, um, with the second approach, we have three major components where only the satellite data is being provided as input, and then we have some layers of neural networks that we're calling common feature transform model. And then it kind of branches out in two different directions. One target is UAS-based canopy attributes, another target is yield prediction model. So the idea is to train this direction first with an assumption that this feature transform model will be pre-trained. So the idea is to take advantage of this pre-trained neural network to help improve the yield prediction accuracy. And the results are even more impressive with a test R square of 0.8. So we also performed some experiments with the independent test site, and the results are close to 0.65 R square. Unfortunately, I don't have those slides with me right now. So the key contribution of this work was this work demonstrated how UAS-based features can be used as a side information to improve satellite-based cotton crop yield estimation. The challenges that we are facing right now is finding the right kind of matching dates between the satellite and UAS data collection, along with how do we remove haze, how do we remove cloud, and how do we get rid of the shadows of the cloud if the cloud is not covering, but the shadow is covering the field. And the additional challenge that we see is the generalization of the machine learning model over independent test set. So this is it from my side. I would be very happy to take any questions now or later on if there is any.
Hey, I don't think it's gonna be feasible to have many questions because we have a lot of speakers that we need to go through today. So if you have kind of very urgent kind of question you really would like to address at this moment, probably you can just go ahead and do that, and otherwise probably we can go to the next speakers.
Okay, does anybody has questions to his presentation from my group?
Okay,
Does
then,
seem so. Yeah.
yeah.
Let's move on. Yeah.
Next, same order as before. Josh, you're next to Akash. Maybe we can go next.
Sure. All right. Hi, everybody. Again, my name is Joshua Carpenter, and I'm only in my second year here, so I don't have quite as much to share as Akash did. But my research focus generally is in the area of two things: object detection and feature extraction from point clouds. And I differentiate those two terms in this way. Object detection would be finding a specific object within the point cloud. And feature extraction would be finding some descriptive characteristics of that object once you've extracted it from the point cloud. So that's generally the path that I'm researching on. And I'll present sort of three projects that fall into this that I've been working on. So the first project I want to present is asphalt core inspection. There's a lot of roadways that need to be inspected to make sure that they've been built to the right specifications. And the way they do that is they drill out a core of asphalt from the road, and they need to inspect that for various properties. And the current way of doing it is they do it manually. They heat up the block, they melt down the asphalt, they use solvents to dissolve the pieces that they don't want, and then they weigh the stones that are left after that process to see how the aggregate or the stones, how they were laid in and in what distributions. So it's manual, it's time consuming, and it's hazardous. We developed a process where we would use images and photogrammetric reconstruction to create a point cloud, a 3D point cloud of the core. I'm going to turn on my pointer here. We'll use images to create a 3D point cloud of the core. And from that 3D point cloud, we'd sort of unwrap that point cloud to create a 2D image of the exterior of the core. And from that image, which shows all of the aggregates and the layers of the core, we want to detect some features about it. And so we wrote, our research developed a way to automatically identify these layers. I have an image here with the red lines representing the different layers that were detected in the asphalt core. And then we also wanted to know the size and distribution of the aggregate within the core. So we have a graph here. This is an output from our program. The red line shows the amount of each size of aggregate in the core. And then we would test that to see if it fell within certain parameters. And you see these little gray boxes here. This is the parameter that the aggregate should fall through. So that line should pass through each one of these gray boxes. And we used that test to classify the size of aggregate that existed inside the layer. So that's one project that I've done some research on. I'd like to do something a little more recent. So this is a current project that I'm working on. We have a photogrammetric point cloud of a forested area. This is a screenshot of that point cloud, and you can see each tree and the major branches are shown in the point cloud. And what we are specifically interested in finding is the diameter of each one of these trees at chest height or at breast height. It's called DBH, or diameter at breast height, and it's a measurement or a metric that forestry folks use consistently to determine the size of the tree. And so we created an algorithm that would slice the point cloud so that we could, if you imagine slicing the point cloud, getting rid of anything above this red box and anything below this red box, you get a little cylinder of points. And then from that cylinder of points, we wanted to detect two things. First, the DBH, like I explained, and then also the center point, the location of the tree. So from that, if you tip that cylinder of points on end, you would get this circle. And if you fit a best fit circle to that, you would get an estimation of the diameter of the tree and a center. So here's a plot of all the centers that we detected. And you can kind of see the shadows of the trees in this plot. And you can see at the base of each shadow, there's a little point for where the tree was detected at. So we were able to detect centers. And then we also wanted to detect the diameter. And we've been having, this is an ongoing area of research. So far, our results, we have great correlation. This red line is a 1-to-1 line where all the points should be if our validation and extracted matched. So we have great correlation, but we're consistently underestimating the size of the diameter of the trunk. So that's an ongoing area of research. The last thing I wanted to present is I'm also interested in detecting the structure of the tree. So current research that I'm working on is taking a point cloud of the tree, and here's a point cloud with a tree feature in it, and trying to detect some of the structure. And here's a drawing with some of the main trunks that have been extracted out from the point cloud. And that's a review of my research. Thank you.
Thank you, Josh. And I
Yeah,
know that there's a lot that because I kind of limited everybody to to be 5 minutes. So I know that Josh, there's a lot more detail that you're working on in between. But thanks for making it a the brief to be within 5 minutes the time window.
Yeah, they are too passionate to be within 5 minutes.
Yeah, if you have any question you want to ask.
I have one question. All three topics are very interesting topics. So maybe the reason that the underestimation in the DBH may be the the tree shapes is not perfect sphere, perfect circle, right? Maybe that's the one reason that the consistent underestimation.
That's one area that we're looking at to see if maybe we could do a best fit ellipse or a best fit some sort of cone shape and come up with some major minor axes descriptor. That's one step further than I presented. Thanks for the
Okay,
thought.
yeah, very, very interesting topic. Yeah, thank you.
Okay, let's move on. Probably, after all this presentation, we'll have a chance to ask questions to anybody, who gave a presentation after after everybody's done. And let's move on. And I think Hansu was the next that I called. Hansu?
Yep. Yep. So, hello again. I'm Hansu Song, and so. Okay, let's move on to my research topic. During my master's course, my main research interests were land cover mapping using Landsat images and solar energy prediction using meteorological satellite image, which is Cheonlian. It's South Korean. And
I think
in Purdue University,
sorry,
my research in
you're breaking out. I'm not sure if it's
really?
me, but everyone else can hear Hans okay, or is only me that the Hans's voice is kind of breaking out?
Yeah, the voice is breaking up to me as well. Yeah.
Okay, I will stop the video, and I hope it will be better.
Okay.
Okay. How about now?
I think it's better now.
Better. Yeah, better.
Okay. So in Purdue University, my research interest is building footprint extraction using deep learning. And specifically, I am trying to address the problem of deep learning for this objective. So I'm trying to address this problem with the public map and LiDAR data. So what I'm focusing on is the two main limitations in deep learning. And the first one is the shortage of the training samples. As you know, deep learning requires a lot of training data, which is the building label for the building footprint extraction task. So if the number of training sample is not sufficient, deep learning may not perform well. And here the problem is that the labeling process is labor intensive and time consuming. So what I'm trying to do is utilize the OpenStreetMap, which is a popular public map. And specifically, I'm developing a method that can automatically focus on the good labels, only good labels in OpenStreetMap. And this is the OpenStreetMap building label over West Lafayette, which is the city where Purdue locates in. And as you can see, the raw OpenStreetMap is incomplete and inaccurate. So not all labels in OpenStreetMap improves the performance of deep learning model. So my plan is to automatically filter out the corrupted area during the training process. As deep learning model takes an input as a patch, not a whole image. So for the deep learning, the image and the corresponding building labels should be split into several patches like this. So naturally, some patches are more accurate than others, and some patches are more incomplete and inaccurate than others. So I'm trying to discriminate those noisy or clean labels. How to do is, first, I plan to train deep learning model with the whole training samples for a while. Then I assume that the temporal model has some ability to rank the quality of the building labels of each patch. Then we plan to filter out the several word samples during the training process. So by doing this, we believe that the model can automatically filter out the corrupted samples, and at the end, only good samples will be left. And the left clean samples will be used to train the deep learning model for a longer period. And this is the one implementation of my model. This is the aerial imagery, and the purple label is the corrupted map, which is used for the training. As you can see, this label is from my model, and this label is the generated map from the basic model, baseline, which is the baseline. So during the training, as the map is corrupted, both models are confused to predict the accurate map. But during this, at some point, this model, my model, do not use these samples as it find out it is a corrupted one. So at the end, my model can predict more accurate map, as you can see in the ground truth map. But the baseline model is ended up to be overfitted to the corrupted map. And this is the second, one I'm focusing on. I will focus on later on, and which is the problem of the poor generalization ability of deep learning. And for example, if deep learning model trains with images of Indianapolis, then try to map the residential area Chicago, it won't work well, as those areas are not similar. So, I thought this is because of the atmospheric conditions or the sensor specific features. So I'm trying to use LiDAR data, which is not sensitive to the area or image acquisition condition. And so I believe the LiDAR-based features will help to improve deep learning performance. So And that's all I have prepared. And if you have any questions, please let me know.
Professor, I think you are muted.
Sorry. Thank you, Hansu. I didn't know that. But thank you, Hansu, for giving a presentation. I know that there's a lot more that you probably want to share, but you just reduce down to a small number of slides. But the first part that Hansu presented, we are working on a manuscript right now, and I think it is almost ready to submit. So hopefully we can get that one published soon, so that you guys can see from the journal as well.
Already, it's just been 1 year, but you
Yeah.
completed one manuscript. Wow, it's a great progress.
And I think the figure that Hansu is showing is going to be the key highlight of this in a manuscript that he's working on right now.
Yeah, different line means a different epochs, right? The evolution of it's iterating, right? Iterating. And
Yeah, right. Yeah, exactly.
yeah, okay. Thank you. Yeah, impressive results. Yeah.
Yeah, thank
Hey.
you very much.
Mhm.
Thank you. And next up, Nikhil.
Yeah, hello everyone again. I'm Nikhil, and as I mentioned, I just joined Dr. Jung's group here at Purdue. So most of my work is my previous research because I'm still trying to learn how geomatics work, how the data collection works and everything.
Yeah, so before you start, and sorry to Nikhil, but Nikhil's background is in ECE, electrical computer engineering. So he doesn't have a geomatics background. So there's a lot, for him to learn from this fall semester. That's what he was talking about. I just want to clarify that he's not a civil engineer yet, but we're gonna soon, convert him to civil engineer soon.
Mhm.
Thank you, Dr. Jen, for that. Yeah, so Hansu, who just presented his research, and my research are kind of similar. I think, and yeah, as I go on, you'll get more understanding what's the different, what are the similarities. Yeah, so as Hansu mentioned already, that with deep learning, especially supervised learning, we need a lot of labels, and collecting labels in remote sensing is extremely hard. We have to go to places, it's extremely expensive, and then there are people who are specialized and they have to label it. It's a time-consuming, expensive process. Even if the application is same, like building extraction, if we have labels for one city, it's the same application. We again have to label for another city. So I'm just showing an example here. So let's say we have one data set here as a source. Yeah, okay. Yeah, so one data set we have labels available. I'm saying that that's a source, and if we train a model and test it, we get good results. But if we use the same model for a different city, we get really, really bad results. The application is same, building extraction model is good on one data set, but it's performing really badly. So it's a problem of non-transferable model as well. So what's the solution of that problem? One of the solution is domain adaptation. In domain adaptation, we transfer the knowledge we already have from a trained model to another data set so that we can get good results. And domain adaptation can be classified as unsupervised and semi-supervised. Mostly my research has been on unsupervised, where we do not use any labels or ground truth data from the second data set, which is the target data set. And the other solution to those kind of problem of high label intensity tasks and non-transferable transferable models is active learning, which is basically trying to find out which labels are the best labels we have to do label them iteratively. So just basics of and generative adversarial networks or adversarial learning, because most of my research has been based on adversarial learning. It's just so the high level view is there are we have two different convolution neural networks in my case, D and G, generator and discriminator, and they are basically trying to compete with each other and in that process improve themselves. So we input random noise into G and it's learning to make some fake data. And here on the other side of the D, we input a real data, let's say good images we have. And the discriminator is trying to differentiate between which is the real one and which is the fake one. So in the process of doing that, D improves, and as D improves, G is also improving and making better and better fake data. So at the end, the objective is that there is no difference between real and fake data. So first work, I did this work at University of Houston and also extended it for building extraction at Oak Ridge National Lab. But here I'm just going to focus on the building extraction part. So here it's a simple process. Here we have, as I mentioned here before, we already have source data which have labels available. We train a model on it, simple supervised deep learning model. We train on it in step one, I'm calling it as pre-training. And in the next step, I do adaptation, and it's unsupervised adaptation. So for target data, the data which I do not have any labels available, I'm trying to adapt the model towards the target data so that I have good F1 score in this case, or accuracy, or whatever the metric I have. And I use the similar kind of adaptation as I shown before in adversarial learning. And the third step is testing. I have a good target network. It's a CNN, simple CNN, and I'm testing on the test set from the target data. So for the building extraction, the results look like this. So before adaptation is the result when I have a good model on source data, but I'm testing it on target data. So it's showing really bad results. It's just noise, I can say. But as the adaptation goes, it's starting to get improved. And also not only the buildings are being detected, we can also see as the adaptation goes on, there is less and less false positives. And in the final step, the buildings are much more similar to the ground truth. And one more thing to keep in mind here is I'm not using any target data. So this is fully unsupervised model. This is the quantitative results. So before adaptation to after adaptation, it's a decent improvement, but F1 score do not exactly represent the kind of improvement we can see qualitatively in the pictures. I also extended this method for semi-supervised, where I used few labels from the target data to see how much information we can extract from few labels if we assume that we have that kind of labels. And we saw that with fewer labels helps a lot, because the amount of information, like the structural information in case of buildings, can only be provided by the labels. So this is the second method, entropy and boundary-based adversarial learning for domain adaptation. This was the paper published in IGRS 2020. And so the problem with the last method was because of unsupervised domain adaptation, the building structures were not good. I mean, we were able to detect buildings, but the structures, the boundaries were not very good. They're kind of blobs. So in this method, we tried to use boundary as one of the metric and implemented it in our algorithm. And the other metric which we implemented in our algorithm was entropy, Shannon entropy. So it's a similar adversarial learning framework, but here we have two discriminator. One is specifically for the entropy part and the other is for the boundary part. So we can have a better boundary structures. Results were like this. So similarly, the ground truth and so before, and this is the before adaptation part where we are detecting nothing, but as the training goes on, adaptation goes on, we get more and more better and better building extraction. So these are the quantitative results for F-score before adaptation to after adaptation. There is an improvement of 0.06 in F-score. Similarly, F-score, if we directly see the F-score, it doesn't represent the amount of improvement we saw. And we also did the ablation study and found out that entropy and boundary are kind of performing same, but if we join them, they perform better. And this is the active learning paper, which I'm still working with Dr. Lexi Yang at Oak Ridge National Lab. And here, as I mentioned, the problem of labels, the domain adaptation helps, but there is always a limit if we limit the number of labels. But if we know what labels we need, the best labels, as Hansu mentioned also. So this was this active learning process was based on this model. But here we do this iteratively and find out which images we need to label, kind of finding the best images. And we did it on several data sets. One of the data set we used was NIP, and we were trying to adapt on SpaceNet, which is open source. And we found out that we could get the same F-score for about 1/3 of labels, finding out the 1/3 labels and labeling them, as we were getting the same kind of F-score with the whole data set. And for global to Venezuela, it was even better. We did it in like about 25 to 30% of labels, so which leads to a lot of time saving and a lot of money saving if we can get the same kind of F-score with half or 1/3 of the labels. And yeah, that's it from my thesis. Thank you.
Thank you very much, Nikhil. I know that since he just arrived Purdue, I'm going to say a couple of weeks ago, so there's nothing he's going to report in terms of research he has done here at Purdue, but it was in a very good introduction about his past research experiences. He's been with other PIs. So Dr. Kim, I guess this is all my group's presentation. Probably you can take from here and introduce your group's presentation.
Okay, so let's do our group. Yeah, maybe Singya, you'll be the first. So just relax and just keep your pace. Keep your pace. So yeah, it could be 5 minutes, could be 10 minutes, but yeah, just take your pace. Yeah,
sure.
Go ahead.
I think maybe not in 5 minutes.
Okay, that's fine. Yeah,
just in 3 minutes.
Okay.
Can you see my presentation?
Yes.
Your voice is echoing, howling. We can.
1 moment, please.
Okay.
I think it's okay for me.
It's okay.
Oh, really? Oh, now it's what's better. Yeah.
Okay. Let me briefly introduce my research. My research area is remote sensing in forest area. At first, my research is related to the satellite that will be launched in 2025. This satellite is scheduled to be launched by Ministry of Agriculture and Forestry in South Korea, and its purpose is to observe forest and agriculture area. Satellite have the following characteristic. SWAT is 120 kilometer and release day is 4 days. It can be tilt and maximum tilting angle is 30 degrees. And it has 5-meter spatial resolution and 5 channels, blue, green, red edge, NIR. Wavelength and is below chart. My research area is topographic correction for mountain area and first BRDF. First is topographic correction. Satellite image with radiometric calibration provide reflectance image, but there's a difference in reflectance in same mountain area. This is shaded area, this is bright area, but this is maybe same reflectance, but there's not same in irradiance values, so we calculate it to samely. So this is reflectance and upwelling, radiance, downwelling. Irradiance is just for calculating reflectance. So simply introduce, I applied 7 topographic method, and there's a very good image in C correction and SES plus C correction. There's a not good in other method. So I have to more research in this area. And there's next first BRDF. I also research in first BRDF. BRDF, the image on left in a picture of forest in Canada. Left is backscattering image and right is front scattering image. This is same forest, but there's a different reflectance because they have not a Lambertian surface, their actual surface. So we need to observe BRDF, and we observe every geometries and every reflectance to make a BRDF model. And in this study, I used drone matrix 300 RTK and red edge multispectral camera and Gemuse H20 RGB camera. I operating these 2 camera in the same time to make higher position accuracy and IMU accuracy. Gemuse H20 can get positioning data from RTK, so it's centimeter level positioning, but red edge can get position accuracy is higher than 1 meter. So I use 2 images with structure from motion. Red edge image can get centimeter level positioning. And there's a specs of 2 sensors. So model inversion require, I use loss-free BRDF models This model is used in MODIS. So I think this is a very good model to use, make a BRDF. So I need some geometries, solar geometry and sensor geometry and reflectance from each geometries. So I can make a BRDF model conversion. And this graph is this graph is positioning of drone related to ground and position of sun. And this color is this color means reflectance. So I think I have to more research in this area. Thank you.
Yeah, good presentation. Thank you. So any questions from the audience?
How do you quantify? Because I think in your, one of the map that you showing earlier, doing tackling reflectance from the satellite using different topographic, correction algorithm. There are, I think, about 8 different images that were showing. But how are you going to quantify which one is better than the other? Is there any way to quantify?
I
which one is better?
skipping, yes, I skipping, but there's an I I can see just first is I forgot it.
You
In
use the,
English.
I think you use the standard deviation, right? Standard
Yes,
deviation.
standard deviation. Yes,
Yeah.
I use standard deviation, and in this good image have lower standard deviation, but there's a higher standard deviation.
So
Yeah.
your assumption here is that they should be homogeneous.
Yes.
Yeah,
If
they are
you have a
supposed to
less-
be the same forest because in that small area. So they're supposed to have the same reflectance in theory, but
Okay.
yeah.
Hey, thank you.
Okay, thank you. And
Thank you.
let's, yeah, good job. So let's move on to Suyun's presentation. Suyun, can you share your slides?
Yes.
It's howling too, also echoing. Your voice is echoing.
I think it should be okay. I think if someone else's, the speaker might be on. But
Okay, good.
Is it good?
yeah, we can hear you okay.
Yeah.
Okay. Hello, I'm Seung Ko. The topic of today's presentation is estimation of microalgae abundance in mud-flat surfaces of Gunso Bay using optical remote sensing. This data is observed in April 2021. Purpose of my research is various optical remote sensors data are analyzed to estimate the spatial distribution of microalgae present on the surface of the Gunso Bay mudflat. Gunso Bay is Chungcheongnam-duk, Korea as the seawater exchanges between the bay and the sea at this 30 square kilometer have crossed the bay. This is Gunso Bay, and this is the yellow box is Busan, a beautiful city where our university is located. Anyway, Gunso Bay is a suitable place for observing the prosperity of various microalgae dynamics. This is a tower installed by QUREOS like Korea NOAA. We can stay here and study water flows out of the mudflat and comes in water flows. This is Professor Kim and Senior Beck and me. This image was taken on drone. Equipment used for observation are hyperspectral camera and hyperspectral sensor and field fluorometer. I got 10 samples from different spots from Gunsol Bay around the tower, and then divided each one into 5 subsamples, so I had 50 samples total. Two analysis methods were used to indicate the spectral index for quantifying benthic chlorophyll A. It is known that chlorophyll generally observes strongly at 670 nanometer. Both methods took advantage of this property. The first one is continuum removal. The goal is to find the deepest features in the reflectance spectrum. And the second is NDVI. The chlorophyll algorithm was created using the actual chlorophyll and the CR or NDVI index. It is known that most of chlorophyll absorbs blue and red and reflects green. So let's look at the spectra of represented samples in number 4, 6, and 1. It is just that there is more chlorophyll as it is low reflectance and blue band and increases green band and decreases sharply at red band. Compared with in situ chlorophyll, the trend of the graph is similar to the theory. The methods of CR and NDVI were applied using absorption and reflectance characteristics of chlorophyll. This graph shows correlation between Ramsey or hyperspectral image data and chlorophyll. Over correlation coefficient placed between 0.6 and 0.7. This is result of classifying the chlorophyll values in 3 categories: high, moderate, and low concentrated. The first reflectance graph observed using Ramsey, and the second photo of the above CR algorithm graphed onto a hyperspectral image. The table below shows the location, each subsample, and chlorophyll concentration. From the graph, sharply curves get higher concentration in chlorophyll becomes, and the higher concentration chlorophyll means turning into more red in color showing below the graph. And of course, close to blue means less concentration. This picture with CR algorithm applied to the sample, and this picture is NDVI algorithm applied to the sample. As I mentioned earlier, the spatial distribution of high and low chlorophyll can be clearly seen. As I work on this, I found 2 limits to my research. First, the chlorophyll concentration of the sample has a large standard deviation with various patchiness. And second, although this experiment is an algorithm applied to a sample with a diameter of about 10 centimeters, it is also necessary to try it on bulk natural sediments. So I need more field observation and data analysis will be conducted. Thank you for listening.
Yeah, thank you. Thank you for the very nice presentation. Any questions?
So if I understand correctly, what you want to do here is you want to take, either multispectral or high spectral images and trying to quantify the amount of, the microalgae in that specific location. Is a final objective they want to go with?
Yes.
Okay. And I think probably because of the time limitation, I think you're using both spectral and hyperspectral camera on a sample. I think something like in a core, you just extract it out and just bring on the ground and take images. And you also have some lab measurement to, measure how much, the microalgae from the samples and trying to correlate that with some of those, the features extracted from hyperspectral camera. Then also you try to use a multispectral as well.
Mostly, yeah. The two hyperspectral sensor. One is image type hyperspectral camera, and then the trials. So can you show? Yeah, this the hyperspectral camera first. Second is hyperspectral sensor. It's a point sensor.
Oh, okay.
It's not image, but it has higher quality than a hyperspectral camera.
Okay.
So we trust the hyperspectral sense trials more than the camera. So that's why we operate the two at the same time. Okay. And then actually, but although she hasn't shown in this presentation, but we also fly the multispectral UAV. Seungil also so operated the UAV multispectral camera. So we also have the images from the air.
Okay. So you essentially you want to eventually scale this up because I think the result that we are seeing is kind of pretty much sample based. You have a one hyperspectral measurement from point basis where you're just shining those the spectrometer on, but you want to scale up that with UAVs probably, and eventually maybe going all the way up to satellite so that we can look at the large area.
Yeah, sure.
Okay.
Soon also acquired some hyperspectral satellite images. Italy recently launched the Prisma satellite, which is hyperspectral. And so how many scenes did you obtain for the Bay Area, Suyun? How many Prisma scenes, clear days?
Clear days since get 6 days.
6 days, wow.
Yes.
Really. Yeah, we are continuously placing order, but nobody guarantees the acquisition. But we keep requesting the scene acquisition from maybe for more than 6 months, right? So
how about, is that Hyperion still operational?
No, it died.
How about, I think ISS, International Space Station, they had a hyperspectral. I think it's called
Heiko. Yeah, Heiko maybe is still available, but
I think that they had a new one up there. It's called DESIS, DESIS.
German's hyperspectral sensor, you mean?
No, I think DESIS, DESIS. Let me check. Yeah. I'm not sure whether they are already up and running, but this is the one that I found. I just paste in the chat window.
Okay, yeah. There may be a couple more, actually, yeah.
I think this is operational right now, this DESIS.
Yeah, I think so, yeah. The DLR, the Germany Space Agency, yeah.
Okay, thank you.
Yeah, good presentation. Thank you, Suyun.
Oh, I think Josh has a question.
Oh, okay.
I just had a quick question. When you take the image of the sample, did you take that image while you're out in the field under the sun, or did you take the sample back to the lab and image it in the lab?
So did you take the sample image in the field or in the lab?
I sampled in the field and take out the land and take a picture or observe spectral sensor.
I see.
But you're also using the white panel for the calibration.
Oh, right.
I saw that in your images, right next to the sample.
Okay, that's what I was curious about. The calibration. Thank you.
Thank you for the question. Okay. Okay, now let's move on to Taehong, the last presentation of our lab members, because others just started the lab just few weeks ago. So
Okay.
yeah, go ahead. Yeah. Taehong, yeah, I think
Yes.
you. Yeah.
Okay.
By the way, before we start, what is in Korean coralline flat?
I will show you. Okay. Sorry, not now. It's I will show
You know, because if I hear that term in Korean, probably I know what it is. So this is the reason why I'm asking. What is it called in Korean? Do you have a
겐녹음.
Korean term?
겐녹음. Coralline flat is 겐녹음 is in Korea.
Oh yeah, I don't think I heard that term before. Then let's go ahead.
Yes, it's get means is coast. Is
Okay.
녹음 mean is melt. Is this mean is seaweed melt. Coast melt like.
Okay, thank you.
Okay. I'm studying about detecting coralline flats of Jeju and Dokdo coasts based on airborne hyperspectral imaging.
So you mean really coast or actually coast?
Oh, sorry. Yeah,
Typo, yeah.
There should be a in between, right?
Yes.
Yeah.
So it means
See
a
you.
completely different thing.
Mhm.
Yeah, it's like a coastal.
Yeah.
Yes. This is coralline flats. This is a healthy ocean. It's marine forest. First is there is marine forest. It has the following characteristic: various species living and abundant brown algae. If whitening is proceeding, it has the following characteristics: simple species living and few brown algae, and occupied by coral and large influx of sea urchins. This is like a sea urchin. And finally, when the ocean is desertification, it has the following characteristics: coral death, sea urchin death, everything is death. Yes, this is caused by environment change. Environment means is very very kind of a lot of kind. So okay, and next is how to detect the coralline flats. So what does it detect? I will detect brown algae, corals, and sand or rock using I will using the airborne or drone hyperspectral imaging and reflectance of a hyperspectral sensor under the sea. What is important? How to find it is very important. Is how to find the remote sensing reflectance. It is very difficult. So we considering about sea shadow avoidance, deep resolution, depth resolution in profiles, instruments dark readings, surface instant irradiance, and instrument attitude. And this is because I'm studying it now. So thank you for listening.
Okay, thank you. Yeah, Taehyung is still an undergrad student, so he just started this work. So basically, also our lab just started research subject recently, so we haven't done much of work, but we plan to have field work in Ulung Island and Jeju Island this summer. So we are waiting for good weather, and airborne hyperspectral sensor will be flown in this summer, in both locations, so we can acquire the images. And then in the meantime, we will deploy the ship-based field campaign beneath the airplane at the same time. So it'll be very interesting. And then because water is clear, we can see through the water in the shallow coastal region.
I think turbidity is going to be a critical factor here, right? You need to pick a day where water is not turbid. Otherwise, you're not going to see through.
Yeah, turbidity is important, but fortunately, Ulung area has very clear water, particularly in this season, summer.
Okay.
So if you have any questions, yeah, you may raise your hand and ask questions.
Looks like Josh and Akash are discussing something, so they might have some question.
Yeah, we did. We were curious about the bullet point that says reflectance of hyperspectral sensor under the sea. We were curious, is this some kind of submersive camera, or is this, what does that mean?
Yeah, I can answer. Yeah, Taehyung, you can answer. Yeah.
Okay. We drop on the sea. My instrument drop on the sea. So we detect bottom of sea. Is it answer? Okay.
Yeah, that's really interesting. I've never heard of that before.
So you're actually putting the hyperspectral camera under the water, or?
Right.
Okay.
Yeah, hyperspectral sensor.
What kind of sensor are you going to use? Because the hyperspectral, I think they're mostly push broom.
We will use a push broom. No, it's just a spot sensor.
Okay.
Its name is TRIOS like.
Okay. Spectrometer,
yes.
not the actual, the scanner.
Oh.
Yes, right.
Okay. So you're gonna get the point measurement, not the images.
Yes, right.
Okay.
Right. The one that Suyun just showed, the TRIOS Ramses is the hyperspectral point sensor that most ocean color scientists use frequently. So that's why it's waterproof, 100% waterproof.
Okay.
And it also has two different calibration files, one for the air, one for the ocean, oceanic water. Okay. So we can use it inside the water. So Taehyung designed this frame that holds the sensors, and then we will be working with two divers. So divers will hold the frame and then bring that to the bottom, and then place the frame on top of the target, and then click. We will take the RGB images as well.
I mean, underwater, you mean, right?
Yeah, under the water. Yeah.
Because I think I'm seeing more and more articles coming out about doing a SFM underwater camera, so that they can construct 3D structure underwater. And actually, the AJ, the Engine Chang, he published a paper, using GoPro, submerged and trying to reconstruct 3D, and actually validate some of those, the elevation measurement, compared to.
Oh, really? Yeah, it will be interesting to collaborate with him because it's not difficult. It's not difficult to use the GoPro camera under the water.
But the trick here is that ensuring overlap, that is quite challenging. Plus, underwater you're not going to have a GPS, So
Uh-huh.
not gonna be have those initial estimate of those extra orientation parameters and etc. is not available. So I believe how what AJ did earlier was that he actually I might have some photos. I remember it'll take some time for me to find it out, but he bought the long sticks
Okay.
mount the GoPro camera at the bottom of the sticks and mount the GPS on top of the sticks so that he just take a photos every 1 second. Actually, he was on a tour boat because in San Antonio they have a San Marcos where they have some the clear water tours where they can see through the glass bottom of the boat so that is they can see so he just kind of submerged the camera on a tour boat and that he just followed the path and we constructed video out of it.
I see. Okay, interesting.
But I think what he's trying to do here is mainly relying on spectral information. But I think structural information is another important features that you might be able to use because based on the pictures that are shown in the slide, and I can clearly see that the healthy the marine the forest has a lot more diverse structure there, but it is going to desertified is becoming more simpler or the smoother surface. So using either sonar or the bathymetric lidar, I'm not sure if you guys have considered that could be another option to quantify those kind of information.
Yeah, maybe we can apply Akashi's work defining the finding out the tree structure stuff that's they can be applied to the seaweeds and corals in a similar manner. Yeah. So good. This is collaboration. Synergy.
Thank you. I think we went through all the presentation that we prepared today. Yes.
Okay.
So anybody has any question that you were not able to ask because of the time limitation earlier, to anybody?
Yeah, it's time for you guys, students. Yeah. Any questions to anybody?
I realize that this is always the most quiet moment of the meeting. Whenever you open up the stage for questions, become silent.
Yeah, I know. I know. Same everywhere.
But I do understand that we have a lot of topic we discuss, and without too much the detailed information. So probably it's not the easiest environment to ask questions at this moment with too little information.
Yeah, maybe from the next time we can focus on individual work one by one, so that we can have deeper questions to individuals.
Probably, I think Dr. Kim, what we agreed upon is that probably want to do this meeting every quarter. So maybe we can prepare one the presentation that has more details from each group, so that in the first hour maybe we can spend about 30-40 minutes for presentation and use another 10-20 minutes for the Q&A. And go to your group, and your group give us a more detailed presentation for same 30-40 minutes and the Q&A session afterward. I think it might be good.
Sounds great. Okay. Sounds great. Yeah.
I think we initially named it as radiometric calibration workgroup. Probably we don't need to do that because we're gonna talk a lot more than just radiometric calibration. I guess by looking at all those different topics of presentation that is presented today, I think we can open up the the possible areas of the discussion more wide open.
Okay, sure. Okay, so thank you for waking up very early for this meeting.
Thank you for staying late at night, because I believe it is already 10:45 p.m. over there.
Yeah, in Korea.
Yeah.
So
hopefully we can have we start with this, but maybe we're gonna have a chance to get together sometime as well,
Yeah, physically, yeah.
face to face. That'd be
yeah.
great.
So it was very nice to meet you all today, and then maybe let's see you in the next time, maybe in 2 or 3 months later.
Okay.
Mhm.
Thank you very much.
Yeah, thank
Have a good
you.
evening. And Akash
Have a
and
good
Josh,
day.
I'll meet you guys soon.
So,
Okay.
okay.
Bye-bye.
Have a good day. Yeah, bye.
Bye.
Bye. Bye.